Acid-base and gas evolution reactions are two classes of reactions that can happen when you get the anion from one reactant combining with the cation of the other. In an acid-base reaction, you have an acid reacting with a base, and this causes those two to neutralize each other, and so these are often called neutralization reactions as well. When an acid and a base neutralize each other, generally water is produced, and an ionic compound that's soluble. Sometimes instead of water, you can get a weak electrolyte being produced. A gas evolution reaction, as its name suggests, evolves a gas. So the combination of the reactant and product combination of the two reactants give us a product that is a gas. And this is often observed as a bubbling or a fizzing of the solution. So we've talked about one definition of an acid, and now we're going to put a name to that. This is the Arrhenius definition, named after the scientist. So a substance that produces hydrogen ions in aqueous solutions. So HCl, when you put it in water, ionizes to form hydrogen ions and chloride ions. We've talked about that. We need to discuss this hydrogen ion a little bit more. If we think about a hydrogen atom, how many protons does it have? How many protons? One. How many electrons does a hydrogen atom have? One. So when it forms a +1 ion and loses an electron, how many electrons does it have? 0. It's got one proton, no electrons, no neutrons. A hydrogen ion is a bare proton. This is not going to be hanging out by itself in solution. It's very, very reactive. And so what happens is the hydrogen ion is not found by itself. It will actually attach itself to a water molecule, and we get this H3O plus ion, which is called the hydronium ion. So I think of the hydrogen ion is, he's a smaller version of the smallest element, right? Crazy small. Not going to be out by himself. He's going to ride piggyback on the water molecule. It's a little bit, like a 3-month-old baby. Do you see 3-month-old babies walking around on the sidewalk by themselves? No. For one thing, they can't walk. But it's very irresponsible to leave a tiny baby like that just outside alone, right? It just doesn't happen. So this is like a very tiny baby, not going to be alone in solution. It's either going to be held by the chlorine or by the water. So what's really happening is we've got hydronium ion in the solution. That's what's really happening. It makes the chemical equations a lot more complicated. And so we often use H plus and H3O plus interchangeably. We just understand that anytime we refer to H plus and it's in an aqueous solution, we just understand that that's actually sitting on top of a water molecule and it's not by itself. So we use them interchangeably, and I understand that that can be confusing, and I'm sorry. So an acid like HCl can release one hydrogen ion, one proton. So that's a monoprotic acid. It releases one proton. Polyprotic acids can release more than one proton. So they have more than one ionizable hydrogen ion, and they release them one at a time. So sulfuric acid, H2SO4, is a diprotic acid. 2 protons is what that means. It has 2 hydrogens at the beginning of its formula. It can release them one at a time. The first one is a strong acid. The first hydrogen ion, the first proton will come off. It ionizes completely. The second hydrogen will ionize only partially. It's weak. So I don't have a picture of that. Let's just show you what happens there. So H2SO4, when we put that in water, one hydrogen ion coming off will give us that hydrogen ion and the hydrogen sulfate ion. This reaction happens completely. Now this hydrogen sulfate ion also has an ionizable hydrogen on it. But that does not ionize completely. That's a weak acid. And so that's where we do that double-headed arrow, goes both ways. You can get a hydrogen ion and a sulfate ion. So sulfuric acid is a strong acid, but only in its first hydrogen ion. Any questions? It's kind of confusing.
So when it has 2 on it, it's not as harmful?
When it has a 2 on, is it not as harmful? That's an excellent question. It's easy to mix up strong and weak acids with strength of corrosiveness or how dangerous they are. A strong acid is not necessarily more dangerous than a weak acid. It has a lot more to do with the concentration of the acid. A highly concentrated weak acid is far more dangerous than a low concentration of a strong acid. So it depends. Because you have strong acid in your stomach. Hydrochloric acid is a strong acid. It's completely ionized. There's hydrogen ions and chloride ions in your stomach. And that's necessary for you to be able to digest your food.
Is H3O plus heavy water?
That's another great question. Is H3O plus heavy water? No, it isn't. Heavy water is water that contains one of the other isotopes of hydrogen. There's deuterium and tritium. Deuterium is a hydrogen atom that has 1 proton and 1 neutron. So its mass is twice as much as a normal hydrogen atom. Tritium has 2 neutrons and 1 proton. And so usually heavy water is, we write the formula as D2O, D standing for deuterium. Yeah. Let's talk about bases. The Arrhenius definition of a base is a substance that produces hydroxide ions in aqueous solution. So sodium hydroxide is a soluble ionic compound, and it will ionize, it'll dissociate completely, forming sodium ions and hydroxide ions. So that's a base. It forms hydroxide ions. Other bases, like ammonia, we look at ammonia and we think, well, how is that a base? How does that produce hydroxide ions? It doesn't have any hydroxide in it. It produces hydroxide ions by pulling, that should be a superscript there. It produces hydroxide ions by pulling hydrogens off of water molecules. And I think we'll have an illustration of that coming up. Some bases will produce 2 moles of hydroxide ions per mole of base. So we learned that barium hydroxide is slightly soluble. It's somewhat soluble. Well, when you put that in water, you get a barium ion and 2 hydroxide ions. So every mole of barium hydroxide gives you 2 moles of hydroxide ions. In an acid, that would be called a diprotic acid. We don't have a name for this in terms of bases. I don't know why. But that's an example. So the hydrogen ion produced by an acid can combine with the hydroxide ion from the base, and that makes water. So the cation from the base will combine with the anion from the acid to make a salt. So what we have here is the same idea of swapping partners, that hydrogen and chloride came to the party and sodium and hydroxide came to the party, and they're going to mix it up and see how people get on with each other. So the hydrogen ion and the hydroxide ion will go together, and they're going to make water. You get hydrogen ion and hydroxide ion, and if you just look at their charges, you say push them together, and you might write, say, well, you push those together and you've got HO. Well, that looks a little funny, doesn't it? because we don't usually write it that way, is H2O. And so the hydrogen and the hydroxide are going together, and then we have the sodium ion and the chloride ion going together. So that makes the NaCl. From solubility rules, we know that that's soluble, aqueous. Water is not aqueous, because how can water be dissolved in water? Water is water. Water's a liquid. And so it's a molecular compound, but it can be formed by combining a hydrogen ion and a hydroxide ion together.
Would that water be drinkable?
Yeah, yeah. It's water, same as all other water, very drinkable. So if you do this precisely, so that you have the correct molar amounts of hydrochloric acid and sodium hydroxide, either of which would be dangerous to drink, right? Sodium hydroxide will dissolve your esophagus, really bad news. Hydrochloric acid, depending on how strong it is, could cause you some problems or not. If you mix these two together in a stoichiometric ratio, you're going to get salty water, which isn't going to taste good, but it's not going to hurt you. If we write the molecular equation, well, this is the molecular equation. If we write the total ionic equation and then cross off the spectators, we find that the net ionic equation is H plus OH minus goes to water. This is true for most acid-base reactions, as long as we form an ionic compound, a salt, that is soluble. So here's illustration. We're mixing HCl, aqueous, so aqueous hydrochloric acid. We've got chloride ions, and we have hydronium ions. The hydrogen ion from the HCl is riding piggyback on this water molecule because it's too small to get around by itself. And here we have the sodium hydroxide that dissociates completely. It's a soluble ionic compound. We have sodium ions. We have hydroxide ions. So this hydroxide ion is like a water molecule that's missing a hydrogen ion, right? And here's a water molecule that has an extra hydrogen ion. And so this one says, hey, you've only got one hydrogen here, take this extra one. And that reacts and forms another water molecule. It evens itself out, right? And then what we've got left in terms of ions are just sodium ions and chloride ions. And they're not going to do anything, they're just going to keep floating around. Any questions? These are some common acids and bases. Here are the 6 strong acids that were missing from our earlier section. Those are the strong acids. And again, you need to memorize those. There's 6 of them. It's not too bad. Dentist's office calling me. I can wait. 6 strong acids. Here are some common weak acids, and it says here weak acid. So even if you printed this out in black and white, those are the weak acids. Formic acid, that's the acid that's in fire ants. Have you guys been bitten by a fire ant? Oh man, that stings. And it stings and stings and stings. They inject formic acid into your skin. That's why it stings so bad. Acetic acid, this is the active ingredient in vinegar, and that's what gives it its distinctive smell. Hydrofluoric acid is also a weak acid, and that stuff is actually very dangerous. It will etch glass. It will dissolve glass. So you don't want to mess around with that kind of stuff. Over here, some common bases. Notice that all of these guys here are metal hydroxides. Sodium, lithium, potassium hydroxide, we know from our solubility rules that those are soluble. Calcium hydroxide, barium hydroxide, these are also soluble. Not as soluble, but they do dissolve. And so those are strong bases. They will dissociate completely. Ammonia is what is called a weak base. It doesn't contain hydroxide ions, but it does produce hydroxide in a reaction. So I know this is kind of tiny down here. Ammonia molecules plus water, the ammonia will steal a hydrogen ion from the water, leaving water as hydroxide ions. We have the double arrow here because this does not happen completely. It goes both ways. So it only happens to a small extent. But ammonia does produce hydroxide ions, so it is a base. Any questions? We should be able to write equations for acid-base reactions involving strong acids. So write a molecular and a net ionic equation for the reaction occurring between aqueous HBr and aqueous LiOH. So here we're given the chemical formulas. So that's makes it a little easier, right? Well, HBr, they're telling us it's aqueous, so that's easy too, plus LiOH. And that's aqueous. So we need to predict the products. We're going to do this in the same way we did it for precipitation reactions. We're going to look at the ions involved, swap partners, put them back together. So in HBr, we have a hydrogen ion and a bromide ion. In lithium hydroxide, we have a lithium ion and a hydroxide ion. Again, these are going to split into two ions, one cation, one anion. Then we're going to swap partners, put lithium and bromide together, put H plus and OH minus together. So rewrite them over here, H plus and OH minus, Li plus and Br minus. Okay, so we're going to stick these together, hydrogen ion and hydroxide ion. If you just shove them together, you get HO, which looks funny, so that's water. So that's H2O. What's the state of water at room temperature? Liquid, not aqueous. LiBr, plus 1, minus 1, we put those two together. Is lithium bromide soluble? Yeah, all lithium compounds are soluble. AQ. Okay, so we've got our products. We need to balance the equation. You can look at that and you're like, oh, that one's already balanced. Nice, right? That's the molecular equation. Now they want the net ionic equation. Most acid-base reactions have the same net ionic equation, but let's actually go through it and write the net ionic equation and figure it out. We are not asked to produce the complete ionic equation. So I'm just going to write a sketchy one without necessarily putting all the state symbols in there, because that does get tedious, doesn't it? So these little notes I made down here, those are really helpful for writing the complete ionic equation, because we've already got all the ion formulas. So the HBr makes hydrogen ion and bromide ion, and a lithium hydroxide makes lithium ion and hydroxide ion. And I'm just leaving off all the aqueous state symbols. Over here, H plus and OH minus. But when we write an ionic equation, if it's a liquid, solid, or a gas, we don't split it into ions. So H2O needs to be written as H2O liquid. That's not ionized. And then here we have lithium bromide. That's lithium ion and bromide ion. HBr is an acid, and so we need to be a little bit careful with acids, but that's a strong acid, so we do separate the ions for a strong acid. So there's a kind of a sketchy, complete ionic equation. What do we do to get the net ionic? Yeah, we get rid of the spectators, right? So there's a bromide ion on the left and a bromide ion on the right. Nothing happened to her. There's a lithium ion over here and a lithium ion over there. Nothing happened to him. So what we have left is hydrogen ion. Since this is a requested equation, let's put the state symbols back in there. And we have hydroxide ion, and it makes water, liquid. So this is, we'll sometimes abbreviate this, NIE, net ionic equation. Any questions? do another one. This one has a weak acid. So write the net ionic equation for the reaction between aqueous HCHO2, a weak acid, and aqueous sodium hydroxide. Here they're just flat out telling us this is a weak acid. We should be able to recognize this as a weak acid because it's not one of the 6. I wouldn't expect you to know the name of that acid. Well, to write the net ionic equation, yes?
Why did they just have H2 instead of HCH?
That's an excellent question. Why is this HCHO2 instead of H2CO2? Because this only has one hydrogen ion that can become an ion. This hydrogen will not ionize. So if it was written H2, that would suggest there are 2 ionizable hydrogens, but there's only one. So only the hydrogens that come at the beginning will get pulled off. It's a very good question. So what we've got here is me forgetting to choose a pen. HCHO2. And that's reacting with sodium hydroxide. So we need to predict the products. To do that, we need to look at the ions involved. So here, yeah, we're going to get water. Here we've got, it's a funny looking H. Here we've got this hydrogen, that's going to be one ion, and the CHO2 is going to be the other ion. So we're going to get H plus and CHO2. What's the charge on that funny looking ion? -1. We're removing one H plus. There's one of these and one of that funny thing, so this must be -1. If you take one hydrogen off, the remaining ion is a -1. Excuse me. And over here we've got Na plus and OH minus. So we're going to swap these partners. And the H plus and the OH minus give us water. We'll get to the point where you don't actually need to write that down there. Oh, I didn't leave myself much room. And then over here, I've got, what? Oh no, sorry, I was just seeing things that weren't there. Oh my goodness. So we've got the sodium ion and this guy. +1, -1, so we're just going to put those two together. Looks really weird.
What's the name of that?
I believe that's sodium formate. So is that soluble? Yeah, because the sodium compounds are always soluble in this class. So that's going to be soluble even though you don't know what the name of the anion is. So that's going to be aqueous. Is it balanced? Yeah, it is. That's our molecular equation. They didn't ask us for that. They want the net ionic equation. So in the net ionic equation, this is an acid. It's a weak acid. They told us that. Should that be split into ions for an ionic equation? No. Weak acids ionize just a little bit. They're mostly present as intact molecules. So for an ionic equation, HCHO2 would be written as a molecule. Would we separate sodium and hydroxide? Yeah, that's a soluble ionic compound. So we're going to get sodium ion and hydroxide ion. Are we going to separate water into ions? No, it's a liquid. If it has L, S, or G, just leave it alone, copy it down. Are we going to separate this one? Yeah, soluble ionic compound. Metal and some non-metal things. Sodium ion and the formate ion, AQ. That's the net ionic equation. Do we have any spectators? Yeah, the sodium is a spectator. So we cross off the sodium. So the net ionic equation is this acid plus hydroxide ion will give water plus that anion. Could you have this chemical reaction occur as it's written? Could you have a solution of just hydroxide ions? No, you can't. It's like positive and negative charges. Positive and negative ions don't like to be separated from each other. They're willing to swim around in the same beaker, but you have to have an equal number of cations and anions with their charges balancing out. This is, though, describing what's actually happening because the sodium is not participating in the reaction. If we used potassium hydroxide or lithium hydroxide, the reaction would be exactly the same. The lithium or the potassium ions would also not react, they'd just be floating around. They'd be spectators. Any questions? An acid-base titration is a technique, and we'll be doing several titrations in lab. In a titration, you take a solution where you know the concentration, and you react it with a different solution whose concentration is unknown, and the point of this is to find the unknown concentration. So you add the one solution to the other until you get a stoichiometric ratio. So if it's HCl and NaOH, you're going to add until you've got equal moles of sodium hydroxide and hydrochloric acid. That's called the equivalence point. At that point, you can, based on the amount and the concentration of each, the amounts of each and the concentration of the one, you can find the unknown concentration using stoichiometry. Well, how do you know when you've added the right number of moles? That's the tricky part. There are different ways to indicate that. With acid-base reactions, we use an indicator that's an organic compound that changes color in response to changes in acidity or alkalinity. A common one is phenolphthalein, and it's clear in an acidic solution and it turns pink in a basic solution. So at the equivalence point for an acid-base titration, we know that the number of moles of H plus is equal to the number of moles of hydroxide ion. And so we can use stoichiometry to calculate what we need. Here's an illustration and some photographs of an acid-base titration. So here we've got sodium hydroxide in a burette. And we use a burette because we're able to measure the amount of liquid dispensed, and we're also able to dispense it in a very controlled way. We can let out one drop or even part of a drop if we need to. We're not showing the sodium ion because it's a spectator. Here's our hydrochloric acid solution. We're not showing the chlorine because it's a spectator ion. It's not participating. So we know the concentration of the sodium hydroxide. We don't know the concentration of the acid. As we add sodium hydroxide, the hydroxide ions will react with the hydrogen ions. At this point, we still have some unreacted hydrogen ions. We keep adding until we've reacted all of the hydrogen ions. We've added just enough hydroxide ions. At that point, the solution will turn pink. This is what it actually looks like. So you're adding a clear liquid to a clear liquid. Nothing's happening. When you get closer, you begin to see some pink forming, but when you swirl the flask, it goes away. And then one more drop, and it'll be pink. This is an overshot endpoint. It shouldn't be that pink, but pale pink doesn't photograph well, so we're getting the idea. Phenolphthalein is the indicator. That's a mouthful right there. So let's look at how we would do this sort of a calculation. The titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar potassium hydroxide solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? We're going to use stoichiometry to solve this. We need a balanced chemical equation. Well, our two reactants are H2SO4 and KOH. So we need to look at the ions that those form. So we've got H plus and sulfate. We've got potassium ion and hydroxide ion. Is it just me, or do those balances sound like cows? Yeah. Meow. They're like self-leveling or calibrating themselves. It's very distracting during exams. So we look at the ions that the acid and the base contain, and we swap the partners. So the H plus and the OH, that's just going to be water, right? H2O liquid. What we're really interested in is the K plus and the SO4. So K plus and the SO4 2 minus. This has a -2 charge. This only has a +1. So we need 2 potassiums to balance the charge on the sulfate. This is aqueous because all potassium compounds are aqueous. So looking at these ions, swapping partners, that's how I figure out what the products are. I need to balance the equation. Is it already balanced?
No.
No. So the H's and the O's get a little confusing in these. So I would not focus on those. I would focus on the other ions. So here we've got sulfate, SO4, and there's SO4. Here I have 2 potassium ions, and here I have 1 potassium ion. So I need to have 2 potassium ions here to balance the potassiums. Now we can look at the hydrogens. So here I've got 2 hydrogens, and here I've got another 2 hydrogens. And here I only have 2. I need 4. So if I put a 2 here, I'll get 4 hydrogens. The O's should take care of themselves. Realize this is, that O is too small. Let's make it a capital O. But double check. So I've got 4 oxygens here and 2. That's a total of 6 oxygens over there. 2 oxygens plus 4 is 6. Any questions about that? So I'm going to get rid of my scribblings down here because I need that space for numbers. Balanced chemical equation. Now I'm going to take the numbers from the problem and write them under the equation. 20 milliliters of H2SO4. 20.0 milliliters of that. We don't know the concentration. 22.87 milliliters of the KOH. 22.87 milliliters of KOH. And they told us the molarity there, 0.158. Capital M means moles per liter. Okay? We want to know what the concentration of the unknown solution is. Question mark. Concentration, moles per liter. So this is a variation on grams to moles to grams. Mom, where does that come from? Oh. You know, people ask me about next week. You know, what are we doing next week? What are your plans for next week? I'm like, I don't know what I'm doing next week. I don't know what I'm doing right now. Okay, pull it together, Jody. So this is the normal thing, right? But here, we're not given grams. We have milliliters and we have moles per liter. Moles per liter is a conversion factor. So we're starting with milliliters. And what do we want to end up with? We want molarity. Well, what is molarity? Moles over liters. So we know the volume, it's milliliters, but we could convert that, right? So what we need here is the moles of sulfuric acid. And then we can divide by the volume. So we're actually just going to not do that last step. We're going to go milliliters to moles to moles. Okay with that? So I'm going to start with the 22.87 milliliters of KOH. And I'm going to convert that into moles of KOH, and then into moles of H2SO4. And I'm going to stop there. Because I'm going to take that number of moles and divide by the volume and get the molarity. We have milliliters here. We don't have another liter mole conversion over here for those to cancel out. There's a couple of things you can do here. Let's do this. Let's convert this to liters just before we start. So converting to liters involves moving the decimal point 3 places, but you have to do it in the correct direction. This is the smaller unit. We're trying to make it into liters. Liter is a big unit. If the unit's getting bigger, the number has to get smaller. So I want to move the decimal point to the left 3 places. I'm going to get 0.02287 liters. If you keep moving it the wrong direction or that doesn't make sense to you, go ahead and write out the whole thing. There's also another way we can do this using millimoles. And if you're interested in that, I'll show it to you separately or individually. So I converted milliliters to liters, and then I stuck that in there. And now our units are happier, because I've got liters down there that'll cancel, and I've got moles of KOH down here. The mole ratio, again, comes from the balanced chemical equation. 1 mole of H2SO4 and 2 moles of potassium hydroxide. This moles to liters is the molar concentration. Sorry to say the wrong thing. It's the molarity. 0.158 moles to 1 liter. 0.02287 times 0.158 divided by 2. 0.0018. I should have 3 significant figures here. Remember, leading zeros don't count. 6, 7. Oh, what the heck? There's only one more. I'm going to write it down. That's the moles of H2SO4. Everybody okay with that? We're going to divide this by the volume in liters. Well, we've got volume in milliliters. If I want to make that into liters, am I going to make 20 larger or smaller? Smaller. Liter is a bigger unit. I need to make the number smaller. 0.0200. I'm moving it 3 places. 1, 2, 3. So that's my volume. So the molarity is the moles over the liters. So I've got 0.00180673 with 3 sig figs moles divided by the volume in liters, 0.0200 liters.
0.0200.
Yep. So calculator 0.09033365, that's just what all of it says. My volumes, well, this volume had 3 significant figures, and this molarity has 3 sig figs. Those both played into this. So this should have 3 significant figures. I'm going to round it there. And the concentration is 0.0903 moles per liter, or capital M. Any questions? Sometimes students want to use the dilution equation to solve titration problems. Don't do that. Dilution is when you have a single compound and you're adding more water to it, not when you have a chemical reaction. What's tricky is that for some reactions, it actually works. But what it leaves out is the stoichiometry. You're going to lose this dividing by 2, and so your molarity is going to come up twice as large as it should be. Just don't use the dilution equation. Gas evolution reactions, a gas evolves. Sometimes the gas is formed directly, like when we take potassium sulfide and mix it with sulfuric acid, we get potassium sulfate and dihydrogen sulfide gas. This is a gas, so I'm calling it dihydrogen sulfide instead of sulfuric acid, hydrosulfuric acid. It's not dissolved in water here. We could predict these products by swapping the ions, sticking them back together. So that's one thing that can happen. More commonly, a gas is formed by decomposition of one of the products after you exchange the ions. If you take sodium hydrogen carbonate as baking soda and hydrochloric acid, and you mix them together, swap the ions, you get sodium chloride and carbonic acid. Carbonic acid isn't stable. It decomposes. Carbonic acid will spontaneously decompose into water and carbon dioxide gas. This is how we get the CO2 in soda. It's carbonic acid.
Is that why it goes away?
And that, yeah, it goes away because when you purchase the soda, the carbonic acid is pretty much done. The CO2 is soluble in the water because of the pressure on the container, but as soon as you release the pressure, the CO2 starts to come out of the water, and it's just downhill from there. So we need to be able to recognize gas evolution reactions. There's 4 categories here. If you have a sulfide reacting with an acid and you swap the partners, you're going to get H2S. You need to remember that that's a gas. So add that to the list of things to memorize. Here's an example reaction. You predict the products like we've been doing, just swapping partners. When you see H2S as a product, remember that's a gas. If it helps, H2S is a little bit like H2O, right? Sulfur is right below oxygen. And that's forming actually a molecular compound. It's a gas. That's that really nasty smell that you find in like rotten eggs. Bad. Most sulfur compounds don't smell good. And then we have these 3, and these are all sort of similar. So, yeah, question?
You said you need to memorize the whole chart?
Well, just gas.
Well, you need to memorize that H2S is a gas, and you also need to memorize that these 3 are going to decompose into gases. And I'll show you how we can figure out what gases they make without having to flat out memorize it. So if you swap the partners and you end up with H2CO3 or H2SO3 or NH4OH, these are all going to decompose. Thankfully, they do it in the same way. They lose a water molecule. So each of these guys is going to lose a water molecule. if we take H2, H2CO3, and we get rid of H2O. So we get rid of two of the H's and one of the O's. I'm taking H2O out of it. What's left is CO2. We should recognize that carbon dioxide is a gas. So that's a gas. We can do the same thing with sulfurous acid. Take an H2O out of there. Well, that's two H's and one of the O's. That gives us SO2. It's also a gas. NH4OH. Take a water out of it. The gas is what's left. Well, let's get rid of this H and one of those H's and this O. What's left is NH3. That's ammonia, and ammonia is a gas. Okay? So you predict the products by swapping partners, putting them back together. If you see H2S, it's a gas. Write it as such, you're done. If you get one of these, carbonic acid, sulfurous acid, or ammonium hydroxide, that's going to decompose, and so you need to decompose it, and they lose one water molecule, and what's left is the gas. Any questions? Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Hydrobromic acid. The prefix hydro tells me that this is a binary acid as opposed to an oxyacid. So I'm going to have hydrogen and the ion that bromine forms. Whoops. So putting those two together, that's HBr aqueous. Aqueous potassium sulfite. Potassium is K+. Sulfite is the light version of sulfate. So it's SO3, same charge as sulfate. Putting those two together, I need 2 potassium ions to balance the charge on the sulfite. That's also aqueous. Predicting products, we're just going to swap partners. So K plus and Br minus, well, I just need one of each, so that's KBr. Potassium compounds are always soluble, so that'll be aqueous. And then the H plus and the SO3, 2 minus. Well, I need 2 hydrogens to balance the charge on the sulfite. Is this one of those things in the table? H2SO3. Let's go back and look at the table. Yeah, it is. H2SO3. So we need to remember that H2SO3 is going to decompose, it's going to lose a water molecule, and the remainder is the gas. So H2SO3. Well, if I get rid of the H2 and I get rid of one of the oxygens, I'm left with SO2. So here, instead of writing that, I'm going to write what it makes. H2O, which is a liquid, and SO2, which is a gas. I also need to balance the equation. What's one element that's not balanced? You guys are asleep. Potassium. Potassium isn't balanced. There's 2 potassiums on this side and only 1 on that side. So to fix that, I can put a 2 in front of KBr. Let's check this ion then. Br, now I've got 2 of those over here and only 1 over there, so I need a 2 in front of the HBr. And This is an instance where the sulfite ion did not stay intact. It came apart. So I need to look at sulfur and oxygen separately. Here's one sulfur. There's one sulfur. Oxygens, I've got 3 over here. I've got 2 there and 1 here, so that's okay. And hydrogens, I've got 2 hydrogens and 2 hydrogens. So there's the molecular equation. Any questions?